Today we are going to learn lesson 4, factoring polynomials. And learning goals for today is listed here. After this lesson, you will be able to determine if a polynomial is in a factored form and factor a given polynomial using different techniques, including factoring out the greatest common factor, special expressions, or using formulas, trial and error, also known as cross multiplication, and the undetermined coefficients, factoring by grouping, and factoring by using the factorial theorem. We'll talk about the theorem later in this class. And you should also be able to understand the remainder theorem, factor theorem, integral zero theorem, and rational zero theorem, and their applications. So first, let's have a look at an introduction to factoring. And after that, we'll introduce some common methods to factor polynomials. These are the basics to solve polynomials, polynomial equations, and inequalities. So first of all, let me introduce the factoring briefly. Factoring is to write an expression as a product of factors. For example, we can write 10 as 5 by 2, where 5 and 2 are called factors of 10, right? We can also do this with polynomial expressions, okay? So usually the factoring needs to be complete. That means no more factoring possible unless otherwise stated. Also, you should note in this course, the factoring is only considered in the set of real numbers unless otherwise stated. If an expression cannot be factored, it is said to be prime, which means it only has a factor itself and 1, right? Terms occur in an indicated sum or difference. Factors occur in an indicated product. An expression is in factored form only if the entire expression is an indicated product. For example, the first column here are polynomials in factored form, and the second column here are polynomials not in a factored form. You can compare and have a look at this by yourself, okay? All right, now you should have an intuitive understanding to the factoring. Okay, so now let's have a look at the common methods to factor polynomials. So in this course, we'll introduce the following common methods to factor a polynomial. There are 6 methods. So let's have a look at them one by one. First, factoring out the greatest common factor. Greatest common factor is also abbreviated as GCF. The GCF for polynomial is the largest monomial that divides in a factor of each term of the polynomial. This process is basically the reverse of the distributive property. So there are 2 steps. Step 1 is to identify the GCF of the polynomial. Step 2 is to divide the GCF out of every term of the polynomial. Okay, so let's use an example to illustrate this technique. Let's see the following 2 examples. Factor the following expressions completely. So we can have a look at that. Okay, first expression. It is not difficult to see that a b squared c is the greatest common factor of the whole polynomial, right? So we can just put it in front, and what's left in the brackets is a plus 2c minus 3b. Remember that you can always check or verify your result by distribute the common factor back into the 3 terms to get the original expression, right? So if we verify this result, you can see that the expanded form is actually a squared b squared c plus 2ab squared c squared minus 3ab cubed c, which is exactly the same with your original expression. So that means our factoring result is correct. Understand? Okay, now let's have a look at the second example. Okay, this time apparently 3x minus 1 is a common factor, right? So we can just put it in front. So what's left at back is x plus 5, right? So this expression can be factored into this one. Understand? Again, you can also check your result by expand everything back. Okay. All right. Next, let's do some example. Let's do a practice. This time you need to solve this by yourself. Okay. I'll give you 2 minutes to solve them. Okay, finished. First question. Greatest common factor is 2, right? So we can put 2 in front and then x minus 2y plus 1, right? This is the factored form of the polynomial. Next, you can see that 5x squared and y is greatest common factor times the sum of x plus 2y, right? Also, we need to verify if the result is correct. It's better to do this after the factoring, okay? So 5x3y plus 10x squared y squared. Yes, the result is correct. Okay, next technique is called special expressions or using formulas. So please have a look at the following common used formulas and write them down in your notebook if you are still not familiar with them. So we can easily prove all of these by expand the factored form into the expanded form. For example, if we expand everything here, you'll get a squared plus ab minus ab minus b squared. So this is exactly the left-hand side, right? And actually, the factoring process is just a reverse process of expanding. So please have a look at all of these formulas And do remember them because they are very handy. Okay. And for the last statement, if you have a quadratic polynomial like ax squared plus bx plus c, actually we can factor this by completing the square, right? So we can write it like a times x squared plus b over a x plus c over a, and then a times x plus b over 2a squared plus c over a minus b squared over 4a squared. And this is actually x plus b over 2a squared minus 4a squared b squared minus 4ac, right? As you can see here, this is something square minus something square. So we can use a formula, which is equivalent to first term plus the second term. Second term would be the square root of this term, right? Which is 2a the absolute value of 2a and the numerator is b squared minus 4ac. Note that here b squared minus 4ac must be non-negative, right? If it is negative, it cannot be factored in the real number set, right? And next term would be x plus b over 2a minus 2a is the denominator, and b squared minus 4ac is the numerator, right? Because we have a negative sign and a positive sign here, so it is not necessarily to use absolute value here. So we can just leave the 2a there. So actually we can remove the absolute value sign. So this means if we let x1 equals minus b squared minus 4ac over 2a, and let x2 equals minus b plus the square root of b squared minus 4ac over 2a. Then the original expression can be factored to a times x minus x1 and x minus x2. Actually, the x1 and x2 here are the real roots of the function ax squared plus bx plus c equals 0, right? Okay, so I hope you know how to factor special expressions using the formulas now. Okay, let's have a look at an example. Factor the following expressions completely. Okay, this is the original expression. And by observation, we can see that it is something square minus something square, right? So you can use this formula. A squared minus b squared is a plus b times a minus b. Okay, so first step, it equals a squared plus b squared minus 1 plus 2ab, right? Because 4a squared b squared is 2ab squared. Okay, times a squared plus b squared minus 1 minus 2ab. And also note that a squared plus b squared plus 2ab is actually a squared sum, right? of 2 and b, and minus 1. And then a squared b squared minus 2ab is a squared difference between a and b, and then minus 1, right? And then we can use the formula again. This is the difference between two squared terms, right? So this can be factored to a plus b plus 1 times a plus b minus 1. And then a minus b plus 1 times a minus b minus 1. And then this is a final factored term of the original expression. Understand? Okay, let's do a practice. So this time, I'll give you 2 minutes to think about how to factor the following expressions completely. Okay, let's have a look at the solutions. First of all, we can factor out the greatest common factor, right? Which is 3u. If we put 3u in front, what's left behind is u cubed minus 8v cubed, right? Note that we can then factor this using the formula, the difference between 2 cubed, right? So this is 3u times u minus 2v times u squared plus 2uv plus 4v squared, right? And this should be the final solution, the final factored form of the original expression. Okay. All right, let's do another practice. Factoring the following expression completely. Again, I'll give you 2 minutes to solve this. All right, have you finished? So note here this is a quadratic expression, right? So we can directly use the last formula here. First, we need to find the x1 and x2. So note here, this is our a, which is 1, right? This is a coefficient b, which is 4. And this is coefficient c, which is 1, right? So let's calculate b squared minus 4ac first. So b squared is 16 minus 4 times a times c, which is 12, right? 12 is greater than 0. So we should be able to factor this, right? So let's calculate x1 is 2a minus b plus square root of b squared minus 4ac, which is 12, right? And this equals minus 4 plus 2 square root of 3 over 2a, which is a is actually 1, right? Which is minus 2 plus square root of 3. And x2 is 2a, which is 2, minus b minus square root b squared minus 4ac, which is 12. And this is minus 4 minus twice of square root of 3 over 2, which is minus 2 minus square root of 3, right? So the original expression can be factored into x minus x1, which is minus 2 plus square root of 3, and x minus x2, which is minus 2 minus square root of 3. And we can simplify this further into x plus 2 minus square root 3, and then x plus 2 plus square root 3, right? This is a final solution of the original expression. All right, let's see the third technique, which is called trial and error, also known as cross multiplication method. So this is often suitable to factor trinomials. For example, if we have a trinomial like this, how are we gonna factor it? Okay, so usually we'll consider two numbers. First one is the coefficient in front of the highest order, and then the coefficient here. So as you can see here, the coefficient in front of x squared is 1, right? So 1 can be factored into 1 by 1. And 6 can be factored into 1 by 6 or 2 by 3, right? So we need to put these two numbers here. The product of these two numbers equal to 6. And when we check the cross multiplications, suppose this is A, this is B, the sum of the multiplication should equal to the coefficient in the middle, which is 5, right? So as you can see here, it's better to put a 2 here and a 3 here. The product of 2 and 3 is 6. And if you put 2 and 3, 2 by 1 plus 3 by 1 is 5, which is the coefficient right in the middle, right? So this expression here can be factored into two factors. First factor is 1x plus 2. And next factor is 1x plus 3, which is actually x plus 2 and x plus 3, right? Do you understand? Okay, let's see another example. Okay, this time we have a coefficient 6 and another this time we have term 6 and a term minus 12y squared here. So this time, first of all, we need to factor the first one. 6x can be factored to 2x and 3x, right? You need to ensure the product with two numbers is 6 squared. Next, we need to factor the other term here. Minus 12y squared. We need to factor it so that the product of these two terms here should equal minus 12y squared. And then after we do the cross multiplication, the sum of these two terms should equal x and y, right? So this is why this method is called trial and error. We need to try different combinations of these two terms here. So once you are familiar with this, you will have a feel how are you gonna decompose minus 12y squared here. For example, we can factor it into 3y and minus 4y, right? So the product of 3y and minus 4y is minus 12y squared, which is exactly the last term here. And also, if we do the multiplication, cross multiplication here, as you can see here, 2x times minus 4y plus 3x times 3y. This is minus 8xy plus 9xy, which is exactly xy, the term in the middle, right? So this expression can be factored into, this is the first factor, right? 2x plus 3y. And this is the other factor, which is 3x minus 4y, right? Again, you can always verify your result by expanding the polynomial. Okay, if you expand it back, it should equal to the original expression. Understand? Okay, so now let's do a practice. I'll give you 2 minutes to think about the following 2 questions. Factor the following expressions completely. All right, let's have a look at the solutions together. So note that the first term can be factored into either x squared and 15x squared, right? So if you factor it like this, you can see that no matter how you factor the last term, you will not get a 38, right? For example, if you factor the last term to 1 and 7, by cross multiplication, you will not get a 38x squared here. Or if you factor it, if you factor the last term into 7 and 1, you will not get the 38 either, right? So this method, this factoring is not working. So let's try to factor the first term to 3x squared and 5x squared. So this time, in order to get a 38 by cross multiplication, we need to put a 7 here, right? And 1 here. By this way, you can see that 5x squared by 7 is 35x squared, and then plus 3x squared. This is a term right in the middle, which is 38x squared, right? So the first term is 3x squared plus 7. And next term is 5x squared plus 1, right? Okay, so we have done the first one. Next one, again, first we need to factor the first term into, for example, this time we try 2x, 3x, and then factor the last term. And ensure that by cross multiplication, we get the term in the middle. So let's try, if we put a 3y here, 4y here, this is 8xy plus 9xy, which is exactly the term in the middle, right? 7xy, or 17xy, sorry. So the term can be factored, the polynomial can be factored to 2x plus 3y times 3x plus 4y, right? Okay, so let's have a look at the next technique, which is called undetermined coefficients. This technique is usually suitable for factoring the expression with a pattern like this. Okay, for example, let's take this expression as an example. So note that the first part can be easily factored by using the trial and error method, right? So note that 2x squared can be factored to x and 2x, right? X by 2x is 2x squared. And last term, minus 3y squared, which can be factored to 3y and y, actually minus y, right? And then we need to ensure by cross multiplication, 3xy minus 2xy, we need to get the term in the middle, which is xy, right? So the first part of this expression can be factored into x minus y times 2x plus 3y, right? But remember that there are some other terms here. So we can let the original expression equals x minus y plus m times 2x plus 3y plus n, right? We put these two undetermined coefficients here and then expand it. If we expand this expression, you will get the expression here, right? And this expression should be exactly the same with this one, right? Because m and n are undetermined coefficients here. In order to keep the two expressions identical, we need to ensure each of the coefficient corresponds to the coefficient in original expression, right? So first of all, we need to make sure 2m plus n equals 1 here, right? And then 3m minus n is 14 here. And then the product of m and n should be minus 15, right? So the value of the mn should satisfy all of the equations here. And actually, we can solve m and n according to the first two equations, right? According to the first two equations, we can solve that m is 3 and n is -5. And remember that the third equation must also be satisfied. So we also need to put these values into the third equation to verify, right? If we put m equals 3 and n equals -5, you can see that it also satisfies the third equation. So our solutions for m and n worked for the factoring. So if we put m being 3 and n being -5 to the factored form, sorry, not here, to the factored form here, then we can know that the original expression can be factored into x minus 3 plus m. M is 3, right? And then 2x plus 3y minus 5. This is our n, right? You understand? Okay, now let's do a practice. I'll give you 2 minutes to solve this by yourself. All right, have you finished? Okay, let's have a look at the solutions together. So note that the first part of the expression can be factored easily by the trial and error method, right? So x squared can be factored to x, and 2y squared can be factored to 1y squared and 2y squared, right? So by cross multiplication, we can know that, sorry, there's no square here. 2y and 1y and 2y. So by cross multiplication, we get xy plus 2xy, which gives us 3xy, right? So the first part of the expression can be factored to x plus y and x plus 2y, right? But we have some other terms left behind. So we can just let's call this asterisk. Let asterisk, let the asterisk be x plus y plus m times x plus 2y plus n. And then let's expand this expression, which we will get x squared plus 2xy plus nx plus xy plus 2y squared plus ny plus mx plus 2my plus mn. Now let's combine similar terms. First, x squared, and then plus 2xy, 3xy, and 2y squared. And then how many x's? M plus n x, right? So how many y's? Plus n plus 2m times y, and plus m times n, right? So we need to ensure that the coefficient here is exactly the same with this one. So m plus n is 4. And the coefficient here is the same with this one. N plus 2m is 5, right? And also we need to ensure the coefficient here is coefficient here. Mn is 3, right? So by solving the first two equations, we can get actually m is 1, right? And n is 3. And then we put m is 1, n is 3 into the third one to check if these values satisfy the third equation. Apparently this worked, right? So the original expression is factored into x plus y plus 1 times x plus 2y plus 3, right? And then the factoring process is complete. Okay, now let's have a look at the next technique, which is called factoring by grouping. So in some cases, there is not a GCF for all the terms in a polynomial. Usually, if we have more than terms with no GCF, we can try factoring by grouping. Okay, let's see this example. Factoring the following expression completely. So note that the ratio between the first two terms is 3, right? Actually, it's x to 3, right? And the ratio between the last two terms is also x over 3, right? So this means we can group the first terms and the last terms respectively, right? So if we group the first terms, you can see that there is a GCF for the first two terms, which is x squared. And what's left behind is x plus 3. And for the last two terms, if we put the common factor 2 in front, what's left there is x plus 3, right? Then for the next step, we can see that x plus 3 now is a common factor, and then we can put it in front, x plus 3 times x squared plus 2, right? So the original expression can be factored into this. Understand? All right, let's have a look at another example. Okay, for example, for factor the following expression completely. Okay, so this time it's a little bit trickier because the ratio between the first two terms is not equal to the ratio of the last two terms, right? But this time we can detach the second term into minus 2x squared minus 2x squared and try if this can make the ratios equal, right? So if we detach it into minus 2 squared minus 2 squared, the original expression can be expressed as x cubed minus 2x squared, right? And then minus 2x squared plus. So this term here is key, right? We need to ensure the ratio between each of the two terms is similar. So the ratio between the first two terms is x over minus 2, right? So in order to ensure the ratio is also the same for the middle two terms, we need to put a minus 4x here, right? Sorry, should be plus 4x here. And then remember that the original expression has a positive 6x, so the remaining 2x should be added at the back, right? And 2x minus 4. And now note that the ratios now is equal, right? Each of the two terms has a ratio of x over 2. So let's factoring out the GCF for each of the two terms. First two terms, if you put the greatest common factor x2 in front, you will get x squared times x minus 1, right? And middle two terms, if you put x2 in front, what's left there is x minus 2, right? And the last two terms, GCF is 2, and what's left is x minus 2. Sorry, this is 2 here. There's a typo. And now you can see x minus 2 is a common factor, which can be put in front, right? And what's left in the brackets is x squared minus 2x plus 2, right? And we have a trinomial here. Let's check b squared minus 4ac. b squared is 4. Minus 4 times 1 times 2 is below 0. So this expression cannot be factored in the real number set. So we're done here, right? Understand? Okay, so now let's do a practice. I'll give you 2 minutes to think about how to factor the following two expressions. All right, how are we gonna affect this first one? First one is relatively easy, right? If you check the ratio between the first two terms, you will get x over minus 2, right? And if you check the ratio between the last two terms, you also get x over minus 2, right? So we can just group the first terms and then the last two terms. The first two terms have a GCF of 4x squared, right? And what's left is x minus 2. And then minus x minus 2, right? And then you can see that x minus 2 is a common factor which can be put in front. What's left there is minus 4x minus 1, right? And then we can use the formula. 4x squared is 2x squared minus 1, right? using the formula, we'll get 2x plus 1 and 2x minus 1. Right? How about the second one? Second one, we can try different grouping techniques. We can try different grouping possibilities. One of the workable is to detach the minus 3x cubed to positive x cubed, and then minus 6x cubed, then minus 2x squared plus 9x squared plus 3x minus 6x minus 2. The reason why we do this is to keep the ratio between each of the two terms here equal, right? So as you can see here, for the first two terms, if we put the common factor 3x cubed in front, what's left there is 3x plus 1, right? And for the next two terms, if we put the common factor 2x squared in front, what's left there is 3x plus 1, right? And next two terms, greatest common factor is 3x, and then what's left is 3x plus 1. And last two terms, if we put a minus 2 in front, what's left there is also 3 plus 1, right? So by this, we can have a common factor of 3x plus 1. Then we can put it in front. So what's left there is 3x cubed minus 2x squared plus 3x minus 2, right? And this can be further factored by grouping the first two terms and the last two terms, right? Because the ratio is 3 to 2. So first three terms, greatest common factor is x squared, and then 3x minus 2 plus 3x minus 2. And then we have 3x minus 2 is common factor, and what's left there is x squared plus 1, right? And in this way, we can factor the original expression into this. All right. Then let's have a look at the last technique, which is a complex one. Last technique is called factoring by using factor theorem. So first of all, we need to learn what is a factor theorem. In order to do that, we also need to learn some related concept in advance. Okay, so first of all, I'll give you an introductory example. How we are gonna check if one polynomial is divisible by another by using the long division. For example, if we want to check the polynomial 2x squared minus x plus 7, if this one can be divisible by this one. Usually we'll conduct a long division, right? How do we conduct the long division? Just like what we have done in the number division. Okay, so first of all, for the quotient, we can try to land a x, and then we have x times x minus 1, sorry, 2x. 2x times x minus 1 will get 2x squared minus 2x, right? And then find the difference of these two terms. Minus 1 subtracted by minus 2x, minus 1 minus 2x is x, right? Sorry, made a mistake. Okay, let's repeat this. The dividend here is 2x cubed minus 3x squared plus 8x minus 12, right? The task is to check if this dividend is divisible by the divisor x minus 1, right? So usually we'll need to conduct a long division, which can be done like this. x minus 1. First, we can try to land a 2x squared here in the quotient position. And then what we'll get is 2x cubed minus 2x squared, right? Next, we find the difference between these two terms. So minus 3x squared minus 2x squared is minus x squared plus 8x. Next, we try to land a x here in order to get minus x squared and then plus x, right? And then find the difference between these two terms, which is apparently 7x. Then 7x, drag the minus 12 here, and then try to land a 7 to get a 7 here in order to cancel them. And 7 by minus 1, which is minus 7. And then minus 12 subtracted by minus 7 is minus 5, right? So the remainder is minus 5. If we try to use x minus 1 to divide the original expression. So note here we have some terms. The original expression here is called the dividend, and denominator here is called divisor. And what we have got here is called the quotient. And here's number is called the remainder. So if we express it in a product form, we can see that the original expression is the product of the divisor and the quotient plus the remainder. Understand? Okay, so more generally, assuming a polynomial px divided by x minus b, the quotient is qx and the remainder is r. So note here r is a number, right? R must be a constant, otherwise the division is not over it. So if we have these terms here, then we will have the relationship px over x minus b is qx plus r over xb, right? This is called quotient form. Or in other words, the px can be expressed as the product of the divisor and the quotient plus the remainder. Understand? And this is called the corresponding statement that can be used to check the division. And it is apparent that if the remainder r is 0, we can say that px is divisible by x minus b, right? Or in other words, xb is a factor of px, or x equals b is a 0 of px. Do you understand? Okay, so assuming px can be expressed by the product of quotient and the divisor plus the remainder. Sometimes we only care about the value of the remainder r. If r is 0, apparently px is divisible by x minus b, right? So note that both px and x minus b times qx plus r are polynomials, which are continuous for all x belongs to r. So therefore, we can prove that when a polynomial function px is divided by x minus b, the remainder is pb by getting the limits to both sides of the relationship here. Okay, so if you are not familiar with limits notation, it's okay. You can have an intuitive feeling that when a polynomial function px is divided by x minus b, the remainder is pb, right? And using a similar technique, that is to get the limits of the both sides, we also can prove that when a polynomial function px is divided by ax minus b, the remainder must be b over a, right? Where a and b are constants and a is not 0. Therefore, we have the following remainder theorem, which you need to put it onto your notebook because we're gonna use it many times in today's lesson. Okay, I'm gonna read it for you. The remainder theorem states that when a polynomial function px is divided by x minus b, the remainder is pb. pb means you put the value b in the polynomial px and get a value. This is a remainder. Understand? And when it is divided by ax minus b, the remainder is p b over a. You simply put b over a in the polynomial function px, where a and b are integers and a is not zero because denominators cannot be zero. Okay? Please write this down onto your notebook. Okay, so let me set you an example to illustrate what the theorem states. Okay, let's see this example. Use the remainder theorem to determine the remainder when px is given by this expression is divided by x plus 1. Okay, so according to the remainder theorem, the remainder of dividing px by x plus 1 is p minus 1, right? Because x plus 1 can be expressed by x minus 1, right? So px divided by x minus b, the remainder must be pb, right? So px here is divided by x minus 1, the remainder must be p minus 1, right? So we can simply just put minus 1 in px, which is 2 times minus 1 to the power of 3 plus 1 plus 3 minus 6, which is minus 2 plus 1 plus 3 minus 6, which is minus 4, right? Okay, verify your answer using long division. I'm not gonna do this for you here. You can just check the process after the class. If you verify that, you will also get a remainder of minus 4, right? Okay, so now let's do a practice. This time, it is your turn to answer this question. Use the remainder theorem to determine the remainder when px is divided by 2x minus 3. Okay, I'll give you 1 minute to think about this question. All right, have you finished? So according to the remainder theorem, if px is divided by a polynomial ax minus b, the remainder must be pb over a, right? So apparently this is our A and this is our B, right? So B over A is 3 over 2, right? So the remainder must be P 3 over 2. You can just put 3 over 2 into the original expression, which is 2 times 27 over 8 plus 9 over 4 minus 3 times 3 over 2 minus 6, which is 27 over 4 plus 9 over 4 minus 9 over 2 minus 6, which is 27 plus 9 minus 18 minus 24 over 4, which is minus 6 over 4, which is minus 3 over 2, right? So the remainder is minus 3 over 2. Understand? Okay, a clearer writing of the solutions is illustrated here. You can check it after the class. All right, let's do another practice. Determine the value of k such that when this polynomial is divided by x minus 2, the remainder is 8. Okay, I'll give you 2 minutes to think about this question. All right, let's have a look at the solutions. So according to the remainder theorem, let's say this is px. When px is divided by x minus b, the remainder is pb, right? So this time, apparently b is 2. So px divided by x minus 2, the remainder must be p2, right? So p2 is 3 times 2 to the 4th plus k times 2 to the 3rd minus 7 times 2 minus 10, right? And it also tells you that remainder is 8, so the remainder is 8. According to this equation, we can find the value of k, right? So basically, this is 3 by 16 plus 8k minus 24 is 8. So 48 plus 8k minus 24 is 8. So 8k is 8 minus 24, which is minus 16. So k is minus 2, right? Okay, you can also check the solutions on these slides after the class, okay? All right, now let's have a look at another theorem, which is called factor theorem, which comes from the remainder theorem, right? Okay, let's review the remainder theorem, which states that when the polynomial function px is divided by x minus b, the remainder is pb, right? And when it is divided by ax minus b, the remainder is pb over a, where a and b are integers and a is not 0. Apparently, according to the theorem, when pb is 0, that means the remainder is 0, right? If pb is 0, that indicates that xb must be a factor of px, right? Because when you divide px using xb, if pb is 0, the remainder is 0. If the remainder is 0, that means px is divisible by x minus b, right? So similarly, when pb over a is 0, the remainder is 0. That indicates ax minus b must be a factor of px, right? Okay, so basically this means x minus b is a factor of polynomial px if and only if pb is 0, right? And ax minus b is a factor of px if and only if pb over a is 0, right? Okay, please also write the factor theorem down onto your notebook. We are gonna use it to solve some questions. All right, let's see an example. Use the remainder theorem to find factor first for the polynomial px and then factor px completely. Okay, so according to the factor theorem, if we can find a number, for example, pb, that makes pb equals 0, then the difference between x and b must be a factor of px, right? So usually we can use trial and error method. Usually we can test from the simplest number, positive or negative 1. If it does not work, we can then try positive or negative 2 and positive or negative 3, right? We can put these values into px and check if that number can make px equal 0. So luckily this time, if we put 1 into the original polynomial px, we can find that p1 is actually 0, right? So that means we found a number that can make the polynomial be 0. That means x minus 1 must be a factor of the polynomial px, right? According to the factor theorem. Only and if and only if pb is 0, x minus b is a factor of px, right? This is according to the factor theorem. Okay, so this means we have found a factor of px, which is x minus 1. Then how do we get the other factor? We can get the other factor by using the long division, right? So according to the long division, okay, I'll perform a long division here for you. The original polynomial is this one, right? And one of the factor is x minus 1. So first we can land a 2x squared here, which will get 2x cubed minus 2x squared. And difference between these two values is 5x squared, right? 5x squared minus 3x, we can try to land a 5x here, and then you will get 5x squared minus 5x here. And then difference between these two terms is 2x minus 2. And then we can try to land a 2 here, which you will get 2x minus 2. And you can see the remainder is 0, right? So the other term must be 2x squared plus 5x plus 2, right? Which can be further factored using the trial and error method. First term can be decomposed to x and 2x, and the coefficient here can be factored to 2 and 1, and then by cross multiplication you will get 4x plus x, which is 5x, which is the term in the middle. So the other term can be further factored into x plus 2 and 2x plus 1. And the original expression can be factored to x minus 1, x plus 2 and 2x plus 1. Understand? Therefore, this is a factored form of px. Okay, so factor theorem along with long division is useful to factor a polynomial, but how can we find the first simple factor, such as the x minus 1 in the previous example in the first place? That means, how are we going to find this factor in the first place? Trying blindly from x equals positive or negative 1, positive or negative 2, positive or negative 3, sometimes workable, but may not be an efficient way, right? So the solution is to use the integral zero theorem and rational zero theorem. Okay, so let's have a look at these two theorems first. And I'll set you an example of how we're gonna use these two theorems to solve problems. The integral zero theorem states that suppose a polynomial function px has a leading coefficient 1 and the remaining coefficients a(n minus 1, a(n minus 2, all the way to a0 are all integers, and x equals b. B is an integer, is a 0 of px, or in other words, pb is 0, right? Because pb is 0 is equivalent to x equals b is a 0, also equivalent to x minus b is a factor, right? Okay, then first, b is a factor of the constant term a0, and second, of course, x minus b is a factor of px, right? Okay, let's see an example. A polynomial function px, which is x squared minus 5x plus 6, has leading coefficient 1, right? And remaining coefficients are obviously all integers. And we also know that x is 2 is a 0 of px, or in other words, p2 is 0, right? Then we know that the 2 here must be a factor of the constant term 6. And then, of course, x minus 2 is a factor of px, right? Okay, so actually the integral zero theorem can be proved. Okay, so because of the time constraint, I'm not gonna read it, and I'm not gonna prove this theorem for you. You can check the proof after the class, okay? So actually the integral zero theorem can be proved here using the method here. Okay, so next I'm gonna illustrate how we're gonna use this theorem to solve a factoring question. Okay, let's see this example. Factor this polynomial fully. Okay, so basically we want to find a number. Suppose this is denoted as px, right? Basically, first we want to find a number b that can make this expression be 0. Then x minus b would be a factor, right? So according to the integral zero theorem, the number b here must be a factor of the number here, right? Do you understand? If pb is 0, then b must be a factor of the constant form, a constant term, which is minus 6, right? So we can let b equals all possible factors of the constant form, which is positive or negative 1, positive or negative 2, and positive or negative 3, or positive or negative 6. We only need to check these numbers to see if these numbers can make px be 0, right? So usually we'll start with the simplest number, which is 1. If we check p1, we can get p1 is minus 8, which is not 0, right? This is not what we want, so we keep checking. And then we can check x being 2 and put x being 2 to the original polynomial. Luckily that we found P2 is 0, right? So according to the factor theorem, if we find that P2 is 0, that means x minus 2 must be a factor of Px, right? So in order to find the other factor, we can perform a long division here. If we perform a long division, we can see that the other factor is x squared plus 4x plus 3, which can be factored to x plus 1, x plus 3, right? So the original polynomial px can be factored to the product of x minus 2, x plus 1, and x plus 3. Understand? So basically the integral zero theorem help us to find possible factors of the original polynomial first. Okay, now let's have a look at a practice. This time it is your turn to solve this problem. Okay, I'll give you 2 minutes. All right, now let's have a look at the solutions together. So basically, we want to find a factor of this polynomial px first, right? We need to check a number that such that this number can make the polynomial be 0, right? So where does this number come from? According to the integral zero theorem, this number must be a factor of the constant term, right? So we can just let this number be all the factors of minus 18, which is 1, positive or negative 1, positive or negative 2, or 3, 6, or 9, or 18, right? Usually we'll check from the easiest number to the larger number, right? So when we check number 1, apparently this is not the case. It is not 0, right? And then we can check p minus 1. So if we check p minus 1, we can find that this is 1 minus 3 minus 7 plus 27 minus 18, which is minus 2 minus 7 minus 18 plus 27, which is exactly 0, right? So that means we have found a number that makes the polynomial be 0. That means x minus 1 must be a factor, which is actually x plus 1, right? So x plus 1 must be a factor. In order to find the other factor, we need to perform a long division, right? Okay, I'm not gonna perform the long division here. You can check the solution on these slides. Luckily, we can find the other factor, which is x squared plus 2x, x cubed plus 2x squared minus 9x minus 18, right? And then we can further factor this expression here by using factoring by grouping, right? If we put the first in a group and the last two terms in another group, we can see that here x plus 2 is a common factor, right? And then the other factor can be further factored into x plus 2, x plus 3, and x minus 3. So the original polynomial is factored to x plus 1, x plus 2, x plus 3, and x minus 3. Do you understand? All right, let's have a look at a similar theorem which is called rational zero theorem. Rational zero theorem states that suppose px is a polynomial function with integer coefficient and x is b over a is not 0, and a and b are relatively prime, is 0 of px. Or in other words, p b over a is 0. Then we have the following conclusions. First, b is a factor of the constant term a0. Second, a is a factor of the leading coefficient an. And third, of course, ax minus b is a factor of px, right? Okay, an example. Suppose px is 3x squared minus 20x plus 12 is a polynomial function with integer coefficients. And x being 2 over 3 is a 0 of px. Or in other words, p 2/3 is 0, right? And then we know that 2 is a factor of the constant term 12 here. And 3 here is a factor of the leading coefficient 3 here, right? And of course, 3x minus 2 is a factor of px. This is by the factor theorem, right? Okay, so rational zero theorem can also help us to find the first simple factor of a given polynomial. Okay, so let's, yes. So similarly, because we are running out of time, so I'm not gonna prove this theorem for you. You can check the proof for this theorem after the class by yourself, okay? Okay, next, let me set you an example to illustrate how we're gonna use the rational zero theorem to solve questions. Okay, so here is an example. Suppose we have a polynomial Vx here, and we want to factor this polynomial. So basically, we want to find, first of all, the leading coefficient is not 1, right? So basically, we want to find a number which is b over a that makes the polynomial v is 0, right? So according to the rational zero theorem, if there is a ratio if there is a number b over a can be make the polynomial be 0, then b must be a factor of the constant term, right? And a must be a factor of the leading coefficient, right? So we can let b be all the possible factors of the constant term, right? Which is positive or negative 1 or 2, right? And a be all possible factors of the leading coefficient, which is positive or negative 1 or 3, right? So all possible values of b over a is negative or positive 1 or negative or positive 2 or positive or negative 1 over 3 or positive or negative 2 over 3, right? These are the possible values we need to check if they can make Vx be 0, right? Okay, so usually we'll start from the easiest number, which is 1, right? Once you check x being 1 is a 0, if this is a 0 of Vx, you can find that actually x being 1 is a 0 of Vx, right? So this time we get a little lucky. The first number we check is just a 0 of Vx. So x minus 1 is a factor of Vx, right? So then we can try using the long division to find the other factor. Okay, so the original polynomial divided by x minus 1. Using the long division, we find the other factor is 3x squared plus 5x minus 2, which can be factored using the trial and error method, right? So 3x squared can be factored to x and 3x. So minus 2 can be factored into 2 and minus 1, right? And then 6 minus 6 is 5x. Yes, this can be factored to x plus 2 and then 3x minus 1 and x minus 1, right? So the original polynomial can be factored into this expression. All right? Okay, so next it is your turn to complete the practice here. Okay, I'll give you 2 minutes. Okay, so now let's have a look at the solutions together. So basically, if you want to factor this, we want to find a simple factor first, right? In other words, we want note that the leading coefficient here is not 1. So we want to find a number b over a that can make the polynomial be 0, right? And then according to the remainder theorem, ax minus b must be a factor, right? Okay, and according to the rational zeros theorem, this number here, we don't need to guess it blindly, right? We know that if b over a is a factor, is a 0 of px, then b must be a factor of the constant term, and a must be a factor of the leading coefficient, right? So we can just let b be all possible factors of the constant term, which is positive or negative 1 or 2 or 3 or 4 or 6 or 8 or 12 or 24, right? And let a be all possible factors of the leading coefficient, which is positive or negative 1 or 3, right? And then we know that b over a must be all possible ratios between these two numbers, which are positive or negative 1 or 2 or 3 or 4 or 6 or 8 or 12 or 24 or 1/3 or 2/3 or 3/3 or 8/3, right? We need to check these numbers to see if any of them will make px be 0, right? So usually we'll start with the simplest number, p1. So p1 is 3 plus 1 minus 22 minus 24. This is not 0, right? So next, let's check minus 1. P minus 1 is minus 3 plus 1 plus 22 minus 24, which is not 0, right? Okay, next let's check P2. P2 is 3 times 8 plus 4 minus 44 minus 24. Which is not 0, right? Then let's check minus 2, which is minus 24 plus 4 plus 44 minus 24. So this is actually 0, right? So bingo, we have find a number that can make the polynomial 0. So if minus 2 is a factor of, if minus 2 is a 0, that means x minus minus 2 must be a factor of the polynomial, right? Which means x plus 2 must be a factor of the polynomial. Then we'll need to perform long division to find the other factor. You can try to land a 3x squared here. And then minus 5x. And then minus 12, right? Oh, sorry, this is negative 24. And remainder is 0. So the original polynomial is x plus 2 times the other factor is 3x squared minus 5x minus 12. And this one is easy to factor, right? You can just use trial and error method, which is actually can be factored to x minus 3 and 3x minus 4. So this is the final solution. Understand? Okay, so a nice writing of the solution is illustrated here. You can check the solution after the class. All right, so let's make a summary of today's lesson. So now you should be able to determine if a polynomial is in a factored form and factor a given polynomial using different techniques, including the following 1, 2, 3, 4, 5 common methods, right? And last but not least, understand the remainder theorem, factor theorem, integral zero theorem, rational zero theorem, and their applications. I didn't prove all theorem here, but you can check the proof for any of these theorem in the lecture slides after the class, okay? All right, so this is all for today's class. I'll see you next time. Bye.